Section 12.6, the binomial theorem, is all about expanding binomials. Remember, a binomial, bi meaning two terms, so we're looking at something like x plus y to the third power. We could make this, x plus y times x plus y times x plus y. Forgive my handwriting there. X plus y. Could make it something like that, but there's a much easier and much faster way to do that. There's actually two different ways to do it. The first method I think is more common. I think it's easier. It's just a little more simpler, I guess you could say. It doesn't necessarily mean it's faster than the other way, but it's more easier to understand. The first method involves using Pascal's triangle. I'm sure you've seen Pascal's triangle before. I have a poster of it in my classroom. It's up on the front wall there. Pascal's triangle is this, and this goes on forever, this pattern. So this is not the complete triangle. There is no complete Pascal's triangle. It's an infinite series, I guess you call it, or sequence: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on down the line. This is just kind of the basic nuts and bolts of Pascal's triangle. So this first number right here, this 1, this is row 0 here, okay? So row 0, and we're going to use this row when our exponent is equal to 0. So when we have x plus y to the 0 power, well, anything to the 0 power is just 1. Okay, so that's this right there. The next row, row 1. Row 1 is when n is equal to 1. We'll use this. So anything to the first power, x plus y to the first power, is just x plus y, or whatever these two things might be. Row 2 is the 1, 2, 1 row. We're going to use that when n is equal to 2. Okay, and then it goes on there. Goes on from there. So we'll go to blue here. This is row 3. Row 3 when n is equal to 3. That's this one. Row 4. I'm running out of colors. We'll go to orange. Row 4 when n equals 4 is this one, and then we'll go to brown here. The last one here on this picture, row 5, is when n is equal to 5. Okay, so if we're raising something to the 5th power, this is going to be the row we're going to use. And what this does, this tells us the coefficients of our expansion when we actually go through the process. And I have a couple of examples here that I'm going to show you. But a couple of key pieces of information. Each part of the binomial is in every term of the expansion. So it's not going to be picking and choosing where this x goes. Does it go to that one, that one, that one, and the y goes to that one, that one, that one? No, that's not the case. Both parts, the x and the y, or whatever it might be, goes in front of every or after every one of those coefficients. Okay. The exponents decrease in the first part, meaning the first part of the binomial, and increase in the second part as the terms are written out. So this is going to be like x to the 5th, y to the 0, x to the 4th, y to the 1st, x to the 3rd, y to the 2nd, x to the 2nd, y to the 3rd, x to the 1st, y to the 4th, and then x to the 0, y to the 5th. That's how it would look in terms of the exponents. And then if you're ever not sure, the exponents do add up to whatever this exponent is up here. The exponents in each of these terms are going to add up to this as well. Let's do a couple of examples here. Use Pascal's triangle to expand the binomial. So x plus y to the 5th power. If it's to the 5th power, we're going to be using row 5 here. So let me point this out. We're going to be using this row here. So here's what I'm going to do. I'm going to write out the coefficients just as they are written in the triangle. We'll do that in green. So we'll have, this is equal to, so the coefficients are 1, 5, 10, 10, 5, and 1. Okay, the coefficients are going to be there every time. Now, the next part of this, I'm going to take the first term in my binomial, which is the x, and the x's are in every term. So 10x, 10x, 5x, 1x. Now, the exponents on those decrease from left to right. So we start here at the biggest number, so 5, and as we go to the left, we're going to go down 1, 4, 3, 2, 1, and 0. Okay, the next part, the second part of my binomial, the y part in this case, also in every one of these 6 terms. Okay, so there's that. And the exponents on the second part increase as the terms are written. So we start with 0, then go 1, 2, 3, 4, and 5. Okay, now it's just a matter of cleaning things up. So let me switch to purple here. These are all going to be pluses for now. So plus in between each of these terms. Now, there's really not much to do with this specific example because we don't have to multiply anything out a whole lot, because we just have like 1x to the third or 1y to the second. Really, there's not much to do here other than, y to the 0 power. Anything to the 0 power is 1, so this really just kind of goes away. Same thing with this x to the 0 power. Anything to the 0 power, again, just goes away. So I'm going to put this 1, and we still have y to the 5th power. Really, there's not much to do. These 1s right here, the 1 out front on the first and last terms, don't necessarily need to be there. But other than that, there's really nothing to do left to this expansion other than, maybe write it out a little cleaner and not in so many colors. So we can say x to the 5th plus 5x to the 4th y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the 4th plus y to the 5th. And that right there is your expansion. It goes a whole lot faster than writing out x plus y times x plus y times x plus y times x plus y times x plus y and then foiling for 20 minutes. Whereas if you know that it's a binomial and you're expanding it, you can use Pascal's triangle to make this go a whole heck of a lot faster. Okay? Let's try another one here. Number 2, 3x plus 2y to the 7th power. Now, I don't have row 7 on that triangle, but what you can do, you can look it up. You can Google Pascal's triangle, and you can find the 7th row of Pascal's triangle. The 7th row of Pascal's triangle. I'm going to do this in 2 rows because it's just not going to be, it's just going to be too long to do this in 1 row. So the row 7 of Pascal's triangle, I'll write this up here. It's going to be 1, 7, 21, 35, 35, 21, 7, and 1. Those are our 8 coefficients for 3x plus 2y to the 7th power. So I'm going to write this out. I'm actually going to do this vertically. It might actually be easier to do it vertically. So 1, oops, go back to the pen. 1, 7, 21, 35, 35. I'm going to slide this down. 21, 7, and 1. Now, the first term in my binomial, that was in red, that was right here, so that's going to be 3x. So 3x is going to be in each one of these terms. 3x, 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 slide that down, 3x, 3x, and 3x. And again, the exponents decrease on the first term, so we're going to start with 7 and work our way all the way down to 0. 3, 2, 1, and 0. Now, just like in the last one, let me go back and make sure I have the same color. We went to blue, so we'll go to blue. So 2y, that's going to be in every one of these terms. 2y, 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 2y. Make that look a little better. 2y, 2y, and 2y. And with these exponents, they increase from top to bottom, or from left to right if we were going to write it out horizontally. So we start with 0 and work our way up to, whoops, not 7. Well, that's what we're headed to, but the exponents have to add up to 7 in each of these. So 6 and then 7. So what I'm going to do now, I'm going to kind of multiply some of this stuff out. 2y to the 0 power, that's 1. And if I go down here, 3x to the 0 power, that's also 1, so we don't need to worry about that. 3x to the 7th power, we need to do 3 to the 7th and x to the 7th. So what this multiplies out to is 3x to the 7th is going to end up being 2,100 times 2,187, whoops, x to the 7th. And then 2y to the 0 again, that's 1, so we don't need to worry about that. We can make this a 1 if we wanted to. And then we're going to do the exact same thing with the rest of these terms. 3x to the 6th, so this is going to be 7. 3x to the 6th power is 729. X to the 6th. And then 2y is just going to be 2y. And then I'm going to do that with the rest of these terms. I'm going to pause my video as I'm making it. I'm going to fill it in, and then I'll pick you right back up when I'm done with expanding this a little bit. Okay, so I filled in the rest of my multiplying out, evaluating these powers. Hopefully you've done the same. Now, what we're going to do to finish off each of these terms, we're actually going to multiply the numbers together, the coefficients that we can. We put in equal signs here for all of these. So 1 times 2,187 times 1 is going to be, you guessed it, 2,187. Looks like I just have x to the 7th. Now, 7 times 729 times 2. That is 10,000, let's go back to the pen, 10,206, 10,206, I have x to the 6th, whoops, x to the 6th, and y to the, not y to the 7th, y to the 1st, or just y. 21 times 343 times 4 is going to be 28,028,812, x to the 5th, y to the 2nd. 35 times 81 times 8, 22,680. And I've got x to the 4th, y to the 3rd. 35 times 27 times 16 is 15,120. And this is x to the 3rd, y to the 4th. 21 times 9 times 32 is 6,048, 6048. And I've got x squared, y to the 5th. 7 times 3 times 64 is 1,344, 1344, x, y to the 6th. And lastly, 1 times 1 times 128 is 128, and I just have y to the 7th. Now, if you want to write this all out in one nice horizontal line, you can. Honestly, I'm okay with this, because you're probably going to have to write it down in a notebook paper or in a book assignment. If you want to just leave it like this, I'm okay with that. This, hopefully you can see, goes a heck of a lot faster than foiling it out, because this would be a huge pain in the rear to have to FOIL out 3x plus 2y 7 times. It would take you forever, where this didn't take us a whole heck of a long time. If you've got a calculator in front of you, it goes pretty darn quick. I prefer using Pascal's triangle rather than method 2. Method 2 is the binomial theorem. Both methods have some merit to it. I think if you're just expanding something, I think it makes more sense to do Pascal's triangle, but if you like the binomial theorem better, feel free to use that. The binomial theorem is a little more confusing. The binomial theorem says x plus y to the n power is equal to, it's this, x to the n power plus nx to the n minus 1 power times y plus n times n minus 1 over 1 times 2 x to the n minus 2 y squared plus, I'm going to go down a line here, so it's going to be n times n minus 1 times n minus 2 over 1 times 2 times 3 x to the n minus 3 y to the 3rd power plus, and it goes all the way down until we get to y to the n power, because eventually this will become x to the 0. If our n was 5, this would be 5 minus 5 to the y to the times y to the 5th power. This all would eventually cancel each other out to be 1. So again, this notationally looks kind of like a mess, so that's why I'm not necessarily a big fan of the binomial theorem. I like Pascal's triangle better, just because we don't have to deal with as much notation. But really, the same thing is happening here. This is kind of how the entries in Pascal's triangle come to be. So let's try one. I just got one with the binomial theorem. It's not going to take as long as the last example, so let's just kind of put our heads down and get right to it. So use the binomial theorem to expand 4x plus 2y to the 4th power. It's important to know what our n value is. In this case, it is 4. It's our exponent. Okay, so we're going to I'm going to scroll back and forth here, try to expand this out. So x to the n, well, that's pretty simple. This is x, the 4x, so it's going to be 4x to the 4th power plus, let's see, next is n times x to the n minus 1 times y. Okay, so our n value is 4. Let's go back to the pen. 4 times our x value, which is 4x to the n minus 1 power, so 4 minus 1 is 3, times our y value, which is, in this case, it's 2y, the second part of our binomial. And that's it right there. Okay, so there's our second term. The third term plus, what do we got? N times n minus 1, so that's going to be, go back to red, 4 times, let's see, n minus 1. 4 minus 1 is 3, all over 1 times 2. Times x to the n minus 2. Again, x is 4x to the n minus 2, so 4 minus 2 is 2, and then times our y, which is in this case 2y, and that's going to be squared, plus, let's see, hopefully I got enough room for one more term here. So now we are to this part right here. So n times n minus 1 times n minus 2. So n is 4, n minus 1 is 3. Let me get another parenthesis here. 3. N minus 2 is 2 over 1 times 2 times 3 times 4x to the first power times 2y to the third power. You can kind of see how it's related to Pascal's triangle. We'd have the first term with all the exponents, first term with 3 of them, last term with 1 of them. First term with 2, last term with 2, first term with 1, last term with 1. The only difference really is this, how we find this number out front. It's kind of a mess, but we're just going to kind of work with it. This is our last term here. So plus 4 times 3 times 2, eventually it's going to be n minus 3 over 1 times 2 times 3 times 4. And hopefully you can see now that that's going to be 1. And then we'll have, let's see, if we want to keep going, we'd have 4x to the 0 power and then 2y to the 4th power. And that's going to be the last one. And this eventually is going to work into that part right there. So let's kind of clean this up a little bit. 4x to the 4th power, so I'm looking right here. 4x to the 4th. 4 to the 4th power is 256. So this is going to be 256, whoops, 256, not 25x, 256x to the 4th power. That's a really bad 4. Let's try that again. 4th power plus, let's see, 4 times 4 cubed is the same thing as 4 to the 4th, which is 256, times 2 is going to be 512. So 512, I've got 3 x's and 1 y. Let's see, 4 times 3 is 12, divided by 2 is 6. So this right here is 6. 4 to the second is 16. So 6 times 16, 2 squared is 4. So 6 times 16 times 4, that is 384. So this is positive 384 x squared y squared. Hopefully you can see where that comes from. We'll have x squared there and y squared there. The next term here, 4 times 3 times 2. 4 times 3 is 12. Let's see if we can, the 3's cancel, the 2's cancel. We're just left with 4. Okay, that makes it easier. So 4 times 4 to the first is 4. 4 times 4 is 16. 2 to the third is 8. So 16 times 8, that's going to be 128. So 128. I've got 1x and 3 y's. And then lastly, let's see, the 2's cancel, the 3's cancel, the 1 cancels, the 4's cancel, so we're good there. 4x to the 0 power, that's also 1, so really we're just left with the last term there. 2y to the 4th, 2 to the 4th power is 16, so 16 and then y to the 4th, and there it is right there. Again, very similar to Pascal's triangle. I like Pascal's triangle better. We don't have to worry about all the notation. We just need to find which row we're in and then kind of go from there. There is an alternate form of the binomial theorem. It's going to be really useful when we have to find specific terms of a binomial expansion. And it involves sigma notation. We saw sigma notation in section 5 of chapter 12. So here's the alternate form of the binomial theorem. If you have x plus y to the n power, it's the same thing as, so we're going to have sigma notation from r equals 0 to n of, and this is going to be a fraction, it's going to be n factorial in the numerator. On the denominator is going to be r factorial times n minus r factorial times x to the n minus r power, y to the r power. And again, that's a lot of notation, a lot of variables, but a lot of it's going to be plug and chug. Okay, so this is the alternate form of the binomial theorem, and we'll just kind of go from here. We'll try to use this to find specific terms of binomial expansion. So I've got one here. Find the 4th term of 2x minus 3y to the 6th power. It's important to know that the n value here is 6 because we're raising it to the 6th power, just like here, x plus y to the 6th. Those two are both n's, so our n value is 6. So let's plug in what we know. We're going to hold off on the r value for now. We'll just leave it in sigma notation. So we're looking for the sum from r equals 0 to 6 of, let's see, so we're going to have 6 factorial on the top, 6 factorial over r factorial times 6 minus r factorial times our x value is this one, so that's going to be 2x to the 6 minus r power times 3y to the r power. Now the question is, when we're looking for a specific term, what is our r value? So this is how we're going to find every term in our series or our expansion, but we're looking for a specific term. So in this case, what we're going to want to do is we're going to evaluate when r equals what? Well, in this case, r is going to be 3, because r equals 0 is going to be our first term. So our first term is r equals 0. Second term is r equals 1. Third term is r equals 2. The fourth term is actually when r is equal to 3. So when we're given something like this, if we're looking for the fourth term, we're actually going to use an r value that is 1 less than that, and that's going to be every time. Okay, so we're going to plug in 3 for our r value, and we'll just see what we get. So we're going to make this 6 factorial over 3 factorial times 6 minus 3 factorial times 2x to the 6 minus 3 power times 3y to the third power. Let me kind of erase some of this here. We don't need all of this anymore. Let me slide this up. 6 factorial over 3 factorial times 6 minus 3 factorial. That's something you can type in your calculator right away. Let me just make some dash lines so we're separating our work here. 6 factorial over 3 factorial times 6 minus 3 factorial. That, when you boil it all down, that's going to be 20. 2x to the 6 minus 3 power is really the same thing as 2x to the third power, and this is still 3y to the third power. 2x to the third power, so we're still going to have the 20. 2x to the third power is going to be 8x cubed. Notice once you expand this, the exponent goes from outside to inside. This is 2x times 2x times 2x, which is 8x cubed. Same thing's going to happen with 3y to the third. That's going to be 27y to the third power. I just realized I made a mistake. This is 2x minus 3y, so this should actually be negative 3y since we're subtracting, which makes that negative 3y, which makes this negative 3y, and negative 3 to the third power, negative times negative times negative, is a negative answer. Okay, so now I've got my signs organized. 20 times 8 is 160. 160 times negative 27 is going to be negative 4,320. And then I've got x to the third, y to the third alongside it. So this right here is the fourth term of my expansion of this whole mess. So if I wanted to actually write this out, use Pascal's triangle or use the binomial theorem to find a specific value or a specific term in that expansion, you know, I could write it out if I wanted to, but I can just use this alternate form of the binomial theorem and quickly find that it's negative 4,320 x to the third, y to the third.